Hi, so this is now, today we are looking at section 3.2. We are going to determine the range of variable from raw data. We're going to determine the standard deviation from raw data, the variance, and then we're going to use the empirical rule to describe the data that is bell-shaped. So remember, bell-shaped is the normal distribution. It is kind of our goal with our data. So let's get started. So the range of data is pretty much exactly what it sounds like. It is the difference between the largest data value and the smallest data value, and it tells you the range. So you just take the largest value and subtract the smallest value from it, and ta-da, you have it. So let's take a look at, remember our travel times for the employees of a startup web development company. There's 7 of them. So we've got our largest was 43, our smallest is 5, so we would just do 43 minus 5, and so 43 minus 5 is 38. So the range of our data is 38. That's it. That's all you got to do. So just take the largest, subtract the smallest, and you have your range. I guess I already had that on there. Let me do some erasing. Who knew that I already had that on there? Well, apparently I forgot. So 43 minus 5 is 38. So 38 minutes is the range of data. So that's the difference between the largest and the smallest. Okay, so standard deviation. So this is it's kind of a tricky concept, and I'm only going to make you calculate this one time on your own with, and I would never do it with more than 3 or 4 data points. So this is something you're going to be able to do with your calculator, but first I need you to be able to understand it well enough to do it on your own. So standard deviation is a measure of how spread out the numbers are. We use the population standard deviation when our data set includes the entire population, and if it only is a sample, then we would use a sample standard deviation. I will get into that in a minute. So this Greek letter sigma, that is what we use to, this right here is what we use for standard deviation. So you will see that sigma, and I am the worst sigma drawer on the planet. So if your sigmas look awful, that's okay. My sigmas always look awful. So this is our formula, and please, if you can hear the baby crying in the background, I apologize, but this is what happens when you work from home. So you're going to take, remember this right here is mu, that right there is our mean. So we take each data point, subtract the mean from it, and square that, and then you add them all together. So the squares of all of those differences, you add them together. You divide it by the number of observations. So if we, whatever number of data points we have, that's what we divide that by. I'm going to do an example. It'll make a little more sense once I do the example. Once we divide that, then we take the square root of the entire thing. So let's get right to an example so that this hopefully will make a little bit more sense. So I'm going to find the standard deviation of the travel times that we used to find the range. So those travel times that we've used a couple of times, I'm going to find the standard deviation of that population, because remember, that is all of the employees of that tech company. So we'll be using that population. So first, find the population mean of the data set. We did this before. We found this in our last lesson in 3.1. We found that our mean was 24.9 minutes was the average travel time of each of those employees. So that was our mean. I'm not going to calculate that again. You guys have got this. Next, we're going to subtract the mean from each number and then square the results. So this is what that's going to look like. I'm going to do 23 minus, having issues. Sorry about that. Minus 24.9, and then I square that, and that is 3.61. And then I will do 36 minus 24.9, square that. Do it with the next one. Thankfully, I already had this one. And then we have, I'm just going to do each of these. Squared, 1.21, and finally I have 43 minus 24.9 squared, and that is 327.61. Okay, I did that. Now we add all of these together and then divide by the number of values in your data set. I'm going to have to, so I'm going to take, all right, when I added them all together, I got 1412.87. The number in my data set is 7. So I'm going to move this up here because I'm running out of room. So we're going to go up there. And I have, because I have, that was 201.8. Nope, that's really ugly. Try to make this a little bit prettier because it's going to be here forever. There we go. Next, calculate the square root. So I need to take the square root of this. So my standard deviation is approximately 14.2 minutes. So the standard deviation is approximately 14.2 minutes. So this is just telling me how spread out my data is. We know it's pretty spread out because the smallest data point is 5 and the largest is 43. There's a pretty big difference between the shortest distance to work and the longest distance to work. So the more spread out the data is, the larger your standard deviation is. So for example, if my standard deviation was 1.45, then we would know that everything is going to be concentrated in the middle and it's all going to be really close to that mean. This is telling me right here that it is spread out because I'm going to explain what it really means in a minute. So I'll put a pin in that. I'm not going to keep going because I don't want to confuse you. Let's just focus on calculating this, and then we'll talk about some applications of it in a minute. We're going to be using standard deviation this entire class, so I want to make sure you understand what it means. So we'll get there. Put a pin in that thought. Okay, so I did the data point minus the mean, then I squared that result, then I added all of those together, divided by the number of values in my data set, and then calculated the square root. So we're going to do another example. I want you to follow these steps on this next example. So once I bring it up, pause it and see if you can do it, and then come back and we will do it together. So let me get to the next screen. So here we have, these are those test scores. So I kind of laid it out nicely in a table here. So hopefully you can do each piece separately and then do it all together. So go ahead and pause this video. When you come back, we'll do it together. All right. So hopefully you did it yourself. You paused it. So I'm going to kind of move through this quickly. So this says the data point minus the mean. So I do 82 minus 79. And then 77 minus 79. Just keep this all down. 1 minus 79. Whoa, I did something wonky here because I'm not paying attention to what I'm doing. Sorry. So 90 minus 79. 71 minus 79. 62 minus 79. 8 minus 79. So do this with all of them. So I have, this is 3 squared and negative 4 squared. I don't know what I just did there because that is not negative 4 squared. Losing my mind. Okay, Negative 2 squared. 11 squared. Negative 8 squared. Negative 17 squared. Negative. Okay, where am I? 11 squared. Negative 5 squared. Squared. 9. So this right here is 9, 4, 121, 64, 289, 121, 25, 5, 225, 81. Then we need to add all of these together. So I'm just going to take all of these and I'm going to add them together. So when I added them all together, I got 964. Perfect. So then you take that 964, I'm going to divide it by 10 and then take the square root of the whole thing. So I have the square root of 96.4. So my standard deviation is approximately 9.8. Would be probably 9.8%. So that tells you how spread apart my data is. So once again, I did the data point minus the mean, then I squared it, and then I added all of those squares together, divided by the number of data points I had, took that square root, and I got my standard deviation. So hopefully you got that. If not, rewind this or send me a message and maybe I can help you through it. We're going to talk about now sample standard deviation. So sample standard deviation is very similar. You still do the same thing where you take the data point, subtract the mean, but remember our mean with a sample is an x bar and not a mu. And then divide by, instead of dividing by the sample size, we're dividing by the sample size minus 1. There is some explanation, but for some reason I can't remember it right at this time. So we call n minus 1, we call that degrees of freedom. We'll get into this a little bit later about why we call it degrees of freedom. We're going to be using that a lot later, but right now just subtract 1 from your sample size, divide that number by the n minus 1, and then take the square root. This is our sample standard deviation, and we just denote this with a small s. So if I say to find sample standard deviation, I'll use a small s, which is significantly easier to write than a sigma, which I am terrible at. Remember that? I am terrible at using the sigma. So let's do one of these. So here I'm just going to take a random sample of those three employees. So I just use my calculator to choose 3 employees randomly. So we're just going to do, so our mean, remember we're using the sample mean of these three employees. So my x bar is about 22.3 of these 3. Remember, we just add them together and divide by 3. So I'm going to find that sample standard deviation. So I'll do 5 minus 22.3 squared plus 26 minus 22.3 squared plus 36 minus 22.3 squared. So 1 second here. So 5 minus 22.3, this is negative 17.3 squared. So that's 299.29. This one here, 26 minus 22.3 squared is 3.7. And I square that, and I get 13.69 plus 36 minus 22.3, 13.7 squared. And I have 187.69. Add those 3 numbers together. and you have 500.67. So this time, though, we are going to divide by 2 rather than dividing by 3 because it is a sample standard deviation. And then you take the square root of the whole thing. So dividing by 2, I get 250.33. This should be a 0. Take the square root of that number, and I get approximately 15.8. So approximately 15.8 is my standard deviation, or my sample standard deviation on this. So it's really the exact same thing. You're just dividing by a different number. You just divide by n minus 1 instead of n. Now it's really easy to take a sample with 3 data points, but what if I had a ton of data points? Take a look at this. You don't want to do this by hand. So I'm going to get my calculator out and show you how to do this with the calculator. Okay, so we need to determine the standard deviation waiting time for Wendy's and McDonald's and determine which is larger and why. So here are our wait times. We definitely would not want to calculate these by hand, so I'm going to show you what to do in the calculator. So I'm going to hit the Stat button, and remember, Edit is where we can enter in our numbers. I already entered in all the Wendy's numbers. This is the same way that we did it with mean, to find mean and median. Once again, I want to show you how to delete or clear a row if you already have some data in there, because you probably will have something in there from before. So I'm going to go up to the top of here, highlight that L2 and hit clear. Remember, we want to hit clear, not delete. So I have my Wendy's times in there. I hit Stat and go over to Calc. We're going back to one variable statistics. L1 is up here. So if you put in, actually, I'm going to show you something really cool here in a minute. So let's just ignore what I just said. So I have my L1 right there. Let's go down to calculate, hit enter, and I see that my sample standard deviation is 0.738. Remember, S is sample standard deviation and sigma is population. But since we didn't look at every single drive wait time that Wendy's has ever had, all we did was took 30 random samples. That's why we use the sample standard deviation. So I'm going to pause this for a second, and actually I'm going to come right back and we're going to work on McDonald's. I want you to pause your computer or pause the video and put McDonald's in yourself and see if you can figure out that standard deviation. Okay, so I put my McDonald's in the L2, and I did this because I want to show you something kind of cool. So all of my McDonald's are in the L2. So once again, I went to Stat, I'm going over to Calc and hit enter on one variable statistics. So see here how my list is L1. I have McDonald's in L2. So you can see down here, see on the number 2 down here, right above it in blue, nice and pretty, it says L2. So if I hit second, and then 2, this tells me choose the data from the L2 list. So this, I took the data from the L2 list, and you can see the McDonald's wait times are approximately 1.265. So I have my standard deviation for McDonald's, 1.265. My standard deviation from Wendy's, I don't remember what that was, so I can go edit. I can go Stat over here, and I can do second, and over the 1 is my L1, and that, that has me looking at that list again, and 0.738. So now let's take a look at this data and see what we can do with it. So now we have that the standard deviation or sample standard deviation for Wendy's was 0.738. And the sample standard deviation for McDonald's was about 1.265 minutes. So clearly the data from McDonald's is more widely spread, so the standard deviation is larger, because if we go back and look at our data, you can see that we have 0 minutes for McDonald's and we have almost 5 minutes. That's a pretty big range. For Wendy's, we have 0.35, and then we basically have 4 minutes there. So that is a smaller range. So if you were taking a look or trying to decide which fast food restaurant you want to go to based on how reliable the wait times are, you would probably choose Wendy's because they are more, um, they're closer to the mean. So you can take a look at that mean and decide, okay, so it's going to be really close to this amount. So I don't have that mean. I wasn't looking at that on my calculator, and I erased it so I can get the McDonald's data. But you can be a little bit more confident on your wait time at Wendy's than you will at McDonald's. So let's talk about variance. Variance is something I have never found a use for. And I have a bachelor's in math, and I've never found a use for variance. I've taken so many probability and statistics classes, never found a use for it. However, it will be a problem that will be a question that will be asked on your homework, and for some reason, people refer to it. So all variance is the square of the standard deviation. So it's a sample variance or a population variance. So it's sigma squared if it's population, and it's s squared if it's sample. So you will be, so if you're calculating standard deviation, before you take the square root at the very end, that is your variance. That's it. That's all. So I'm going to move on. Okay, we're going to talk about the empirical rule. So if we have roughly a bell-shaped or normal distribution, then approximately 68% of your data is going to be one standard deviation away from the mean. So basically you take the mean and you add the standard deviation to it, and then you take the mean and subtract the standard deviation from it. So that one standard deviation on either side, all of that stuff in between, 68% of your data will be there. About 95% of your data is going to be within 2 standard deviations of your mean. So if you multiply the standard deviation by 2, add it to the mean, and subtract it from the mean, 95% of your data will be found in there. So almost everything. This is very important because we are going to be using the 2 standard deviation rule a lot when we're looking for outliers. So we can also use the empirical rule based on sample data. So instead of sigma and mu, we would use x bar and s. But it's basically the same principle. It's 2 standard deviations away from the mean is where 95% of your data is going to lie. So here's a great picture of it. I highly recommend printing a copy of this out. Having this picture right here is super handy because we're going to be using this a lot. You will need this on your test. You'll need this on quizzes a lot. So here I subtracted a standard deviation and added a standard deviation to the mean. So this is 68% of my data. This right here is 95% of my data. It's 2 standard deviations away from the mean. And then 99.7% of your data is going to be within 3 standard deviations away from the mean. So this is very, very useful. So you are going to want a copy of this printed out. You will find this in your textbook. Find a nice copy of it in your textbook. This is something I refer to all the time because I don't necessarily always remember these little pieces like this 13.5, 2.35. I don't always remember those. I mean, I can come up with them, I can calculate them, but this picture is extremely useful. So we're going to use the empirical rule for these 54 female patients. So we're going to talk about this. So we're going to put all of this into the calculator, determine the standard deviation and the mean. Actually, what's really great is I've already done that for you. So I took all of this. I don't really understand what serum HDL cholesterol is. I don't really know what that is, but I'm assuming that this is something important for healthcare. If you're in the healthcare industry, you probably know about this. So I computed all of this. So first thing you want to do, compute the population mean and the standard deviation. Second, we're going to draw a histogram to verify the data is bell-shaped. I'm going to provide this. So population mean and standard deviation, 57.4 is my mean, and the standard deviation is 11.7. I was kind enough to put this in the calculator for you, and I calculated it already. So here is my histogram. The importance of the histogram is because I can see that this is roughly bell-shaped. And there's a slight skew, but it's not enough that I'm going to worry about it. So it is approximately bell-shaped. So I already did that. So we're going to determine which percent of all patients have a serum HDL within 3 standard deviations of mean, according to the standard deviation. So take a look at this. So 3 standard deviations away from the mean right here, 99.7% will fit there. So what I am going to do here, hold on here, sorry about that. Let me show you how we calculate this. I am having issues. Okay, so we have that, I'm going to go back, 57.4 is my mean, and 11.7 is my standard deviation. So you're going to be asked different numbers here. So my mean is 57.4. So that's this middle line right here is my 57.4. And I'm going to add one standard deviation. So this would be 57.4 plus 11.7. 57.4 plus 11.7. That gives me 69.1. I'm going to add another standard deviation to that. This line right here would be 80.8. So this right here is 2 standard deviations away from my mean here. I'm going to add a third standard deviation to this. This is 92.5. Now I'm going to go the other direction. So I'm going to take the 57.4 minus 11.7. And then I get that this is 45.7. I'm going to subtract another standard deviation from that, and you'll get 34 here. I'm going to subtract one more standard deviation, and this is 22.3. And they're a lot prettier once I'm sorry, I keep doing that. So I have all of these nice pretty numbers here. So something that might happen, so we know that 99.7% of all of our data is between, or is 3 standard deviations away from the mean. So 99.7% of people, of data, is between 22.3 and 92. Whoa, that was really bad. Sometimes it's hard to talk and write. 92.5. So 99% of people are going to fall between these two values of their serum HDL cholesterol. So something that a question on your homework might ask you, it'll say, what percent of people will have their serum HDL cholesterol between 45.7 and between 45.7 and 80.8. You might get a question like that on your homework. So you'll take a look right here, 45.7 and 80.8, and you'll just add these up. You'll do 34% plus 34% plus 13.5%. And you'll add those together. And you'll say, okay, so 81.5% of people will have their HDL serum cholesterol between those 2 points. That's the way that you would ask those questions, answer those questions. So if you have any questions on this, or once you get to your homework, you're confused, click that message instructor button at the bottom and go ahead and ask me, and I will do the best I can to help you out. Have a great day.